During this video, we'll talk about rational functions. So we'll look at our main objective here will be domains of irrational functions, the vertical or asymptotes of a rational function, and asymptotes we'll look at the vertical asymptotes, the horizontal asymptotes, and slant or oblique asymptotes. And if time permits, we'll also look at graphing rational functions. Although I believe that I don't want to make the video too long, so I think I'll leave the graphing of the rational functions for a second part of this video. So when we speak of rational functions, we are talking about a function, some function f of x, and that's, we usually say a n of x divided by d of x, where n of x is a polynomial, okay? And d of x is also a polynomial. But d of x, so it's very important to note that d of x cannot be equal to 0. Sometimes we say it's a non-zero polynomial. So an example of a rational function, so some examples of rational function is f of x equals 1 over x, where x cannot obviously be equal to 0 because the denominator of any function cannot be 0. Or we can have g of x is x plus 1 over x minus 3. Or we can have h of x is equal to x squared plus 2x plus 3 over x minus 1. These are all examples of rational functions. Okay? So a rational function, what we're looking for, has a numerator and a denominator. Okay? Hence the word rational. Some sort of a ratio. And it's a ratio between two polynomials. Now, one of the things that's we want to look at in the rational functions, I said earlier, we want to know, how do we find the domain of rational functions? And as we had talked about somewhat before, when we talked about domain, okay, we are talking about acceptable x values of the function. So when we speak of domain, the domain of the function, we are looking for acceptable x values. Acceptable x values. So algebraically, okay, when we use algebra, one of the things we do is we take the denominator of the function and we set the denominator not equal to 0, and we isolate x or solve for x. So for example, if we take the denominator f of x for this function, if f of x is equal to 1 over x, the denominator x we said cannot be equal to 0, and we solve for x. Well, x is already solved for here. Okay? So if we look at the number line and we take out 0 from that number line, what do we have left? Well, on this part of the number line, we have negative infinity to 0, okay, parentheses next to the 0 because we excluded 0, union with, union. On this part of the number line, we picked up back from 0 going to infinity. So our domain here will be from minus infinity to 0, union with from 0 to infinity. Now, if we look at this function here, g of x, okay? If we look at g of x is equal to x plus 1 over x minus 3. Well, always one of the things we do is take the denominator, set it not equal to 0. So x minus 3 cannot be equal to 0. And now we solve for x. So if we solve for x in this case, we'll add 3 to both sides. And then we said that x cannot be equal to 3. And you probably could have seen that if 3 minus 3 gives 0, so obviously x cannot be 3, cannot be equal to 3, okay? Now, if once again we look at the number line, here is 0 and here is 3. If we take out 3, what do we have left? Well, this portion of the line on the left will give me negative infinity to positive 3, union with from 3 to infinity. And that will signify our domain, or that is the acceptable values for g of x. The same thing will happen for h of x. For h of x, if we look at this function here, h of x is x squared plus 2x plus 3 over x minus 1. We take the denominator, set it not equal to 0, because denominators cannot be equal to 0. And if we isolate or solve for x, we have that x cannot be equal to 1. So I always like to draw the number line so you will see what's happening. If this is the number line and we take out x is 1, we're taking out this value, what's left on the line? Well, we'll have from negative infinity to 1, union with from 1 to infinity. So you will notice that so far on a number line, I've only been taking out a specific value, right? Over here, I took out x is equal to 0. Over here, I took out x is equal to 3. Over here, I took out x is equal to 1. Well, it depends on the function. Obviously, if the denominator is a quadratic, then your domain could possibly be at most 2 values. So let's look at an example of that. Suppose I have a function where the denominator is quadratic. Okay? If I have the function h of x, so here's an example, find the domain, or state the domain. H of x is equal to x plus 2 over x squared plus 7x plus 12, let's say. Okay. Now keep in mind, denominators can never be 0. So what we do is take x squared plus 7x plus 12 and we say that that cannot be equal to 0. Well, now we have this as a quadratic. So what we're going to do is factor. If we factor, we have x plus 3 times x plus 4, not equal to 0. And now if we have the factors, we take each factor, setting them equal to 0, not equal to 0, or x plus 4 cannot be equal to 0. If we subtract 3 in there, we have that x cannot be equal to negative 3. And if we subtract 4 here, we have that x cannot be equal to negative 4. So now on my number line, I'm taking out 2 values. I'm taking out negative 3, let's do 4 first, and negative 3. These are the 2 values that I'm taking out. We don't care about the other values. We know that these 2 values cannot be used. So what's left? Well, on this portion here, I have from negative infinity going all the way up to negative 4. On this region here, I have from negative 4 to negative 3. Okay? And then in this region here, all of this region, I have from negative 3 going all the way up to infinity. And now they are pieces, so I union them, will bring them together. And that will be the domain. This here is the domain. So it all depends on what your denominator is, how many values you get. You will extract those values and write what's left, and what's left is called the domain of the function. Okay? Now, if you have a good idea of the domain of a function, okay, we're now able to talk about asymptotes. Okay? Because the domain sort of help with vertical asymptotes. the domain will help you with vertical asymptotes. So now let's look at asymptotes of a function. Well, generally we look at three types of asymptotes. We look at vertical asymptotes. Okay. Asymptotes of a function. And generally, since we're talking about rational function. Okay. So when we look at asymptotes, we're looking at vertical asymptotes. We'll look at horizontal asymptotes. And we look at slant asymptotes. And slant asymptotes sometimes are referred to as oblique, okay? Oblique asymptotes, okay? Now, an asymptote is a line, okay? Generally, when we put it in a graph, we put it as a broken or a dotted line, a broken line or a dotted line. Most times we see it in textbook as a dotted line. So if you're talking about a vertical line, okay, then we know that the equation of any vertical line is x equals some constant or some integer, okay? For a horizontal line, the equation of any horizontal line is y equals some constant. And for a slant asymptote is the equation of a linear line. These are all linear, okay? So for something that has a slant to it, meaning it has a slope, so for slant asymptote, it's generally in the form y equal mx plus b. So for vertical lines, the equation for vertical asymptote, since it's a vertical, it's going to be x equals some constant c, where c can be any number, fractions, okay, integers. For horizontal, we're talking about y equals some value c. Okay, c is represents some number. And for slant, we're looking at y equal mx plus b. So we have to look, how do we find these asymptotes? Okay. Well, two things to note, or at least we could start out with the vertical, because there's a big relationship between the vertical asymptotes and the domain of a function. Okay, big relationship between them. So you will also note that when we graph these functions, you will see that what happens to the function as we say that x approaches as y approaches infinity at a specific value of c of that function. Okay, so for example, if I look at the function, okay, example, if we look at the function f of x is equal to 1 over x. So we know when we graph 1 over x from your parent functions that we have discussed, okay, from parent functions, 1 over x we know, here's my x-axis, here's my y-axis. For the function 1 over x, we have the graph that looks very similar to this. And notice that x, okay, so for the domain here, x cannot be equal to 0. Right? X cannot be equal to 0. That's the only one number that would not work in this function. Well, if you notice, there's something specifically happening where x is 0. The line x equals 0 will be this broken line that I'm drawing here in blue. Okay? This line here will be the line x equals 0. So, and that is a vertical line, because the vertical line is always x equals some number. Okay? Now, this line here, this broken line, is what we call our vertical asymptote. So once you have the domain, the numbers that you're excluding from your domain, okay, the numbers excluded from the domain, those x values, x equal to those values is the domain of the function. If you have 2, you will have 2 vertical asymptotes. So the vertical asymptotes here, the vertical asymptote is the line x equals 0. Now you will notice that something unique is happening. What happens as f of x, so alternatively we can say, what happens to f of x as what happens to f of x as it approaches the line 0? Okay? What happens to f of x? What happens to the y value as x approaches 0? Well, if x is approaching 0, the y value is going towards negative infinity. And that's from the left side. On the right side, as x approaches 0, okay, the y value is going towards positive infinity. So what we can say here is that y is not approaching 0. As x approaches 0, okay, and I'm getting 0 from here, the y value, and this is from, let's look from the left, okay, the y value is approaching negative infinity. So how do you write it in terms? You don't have to write left. Sometimes what we do, we write a little negative there, meaning from the left side of 0. Okay? You will say that y is approaching negative infinity. And as x approaches 0 now, from the right side, y is approaching positive infinity. So you will notice that this will always happen when you look at the height of the function at a given x value that was taken out from the domain. Okay? And this part here is a little bit more difficult to understand or to see. Rather than graphically, you will see what's happening. So let's look back at this. As x approaches 0 from the left side, so you start out from the left side of the x-axis, and let's say you trace that function, your y value is going towards negative infinity. That's why we write negative infinity here. And now you go to the right side of 0, that's where the little plus sign is. So as you go to the function on the right side and you start to trace the function, you will notice that that y value is going towards positive infinity. Anytime this happens, that is a hint that there is an asymptote at this specific value, x equals 0. Yeah. So you can use that as sort of a guide to know, or a different way of finding asymptote. Okay. Let's look at another example. So we're focusing on vertical asymptote for now. So what happens if I have the function x plus 1? So example, find the domain and vertical asymptotes. So domain and vertical asymptotes of given g of x is equal to, let's look at x, 2x plus 1 over x plus 1. 2x plus 1 over x plus 1. Well, we know how to find domain. For domain, we said that the denominator cannot be equal to 0. So let's do that first. For the domain, x plus 1 cannot be equal to 0. Right? Anytime it's a rational function, domain, the denominator cannot be 0. And we solve for x. So we're minus 1 on both sides. So we said x cannot be equal to negative 1. Well, if we draw the number line and we take out, here is 0, here will be negative 1. If we take this out, what do we have left? Well, our domain that we will have, the domain will be on this side here, okay, would be from negative infinity to negative 1. And then on this side here, we'll have from negative 1, okay, we're not taking out 0, I just put 0 there, so from negative 1 to infinity. And to bring the two of them, we union them. So that will be the domain of the function, the value that we took out. Sometimes we'll have more than 1, so we don't need the 0. The only value we're taking out is negative 1. Okay? Now, the question also asks to find vertical asymptotes. Well, what value did we take out? We took out x equal negative 1. So your vertical asymptote will be x equal negative 1. At x equal negative 1. Okay? And if you look at this function, you will see that if you approach negative 1, right? If you look at the graph of this function, at negative 1, you will have a broken line. At x equal negative 1, you will have a vertical line that's broken. Okay. So what does the graph of this looks like? Well, your graph would look similar to this on this side. And then on the right side, we have our graph that looks similar to this. So you will see once again, from the left side, on the left side, the y value is going towards positive infinity. And on the right side, it is going towards negative infinity. So anytime you approach the y value at whatever vertical asymptotes you have, if those numbers tend to approach some family of infinity, they could both approach negative infinity, both approach positive infinity, or the sign could be different, we say that at that specific value, there is a vertical asymptote. Okay? We definitely have a vertical asymptote. I'm going to do one because both of my examples, they were approaching either positive or negative infinity. So let's look at an example again where both sides will approach positive infinity. Okay? And a famous one for that will be, so same question, just the function changes. Okay. Let's say we have the function now, p of x is equal to 1 over x squared. Okay. So the domain, still the same process, the domain. We know that x squared cannot be equal to 0. Take the square root of both sides to get rid of the square, and don't forget we have a plus or minus square root of 0. So x cannot be equal to plus or minus 0. Well, there's no such thing as plus or minus 0, it's just 0. So this implies that x cannot be equal to 0, right? Which is clearly 0 squared, you will get a 0 in the denominator. So here is that line once again. If I take out 0, what's left? Well, on this side here, we have from negative infinity to 0, not including, so I use parentheses. And on this side here, I have from 0 going all the way to infinity. So this here is my domain of the function. Okay? Now, we also want to figure out what is the vertical asymptote. So what number was excluded at x equals 0? At x equals 0, that is my vertical asymptote because that's the number I excluded. Well, graphically, you will see what I was telling you about. So here's a continuation just to clarify this here. If I look at this function, my graph looks like this. Okay, where this is my y-axis. Here is my x-axis. So as x approaches 0 from the left side, right? If you're along that function and you come towards 0, you notice that the function p of x, the y value is approaching positive infinity. And if you go as x approaches 0 now from the right side, so if you go from 0 from the right side, that y value, p of x, is still approaching positive infinity. So once again, the two values are some family of infinity. Here they're both positive. So that confirms that there is a vertical asymptote at x equals 0. Anytime you have any sort of infinity, positive, negative, both negative, or interchangeable, that verifies that at that given x value, there is a vertical asymptote. Okay? Now, for horizontal asymptote, what I'm going to do is probably use a simple way for you to identify horizontal asymptotes. And what I'm going to do, or what I'm going to focus on here, is looking at the degree of the numerator of the rational function in comparison with the degree of the denominator of the rational function. Okay? So we're on to horizontal asymptotes now. So keep in mind that when we speak of horizontal, okay, so we're looking at horizontal asymptotes. For horizontal asymptotes, we're going to compare the degrees of the numerator versus the degree of the denominator. So we will find by looking at the degree of the numerator versus the degree of the denominator. So you will notice that in the class notes, we said that f of x is equal to some function n of x over d of x. And then I also indicated that n of x is a polynomial, okay, where n of x is a polynomial a n x to the n plus keep going on. And d of x is, I believe I use b of x, bm, yes, bm x to the m power plus whatever. So when we talk about the degree of the numerator, that's really this n value here, okay? And the degree of the denominator, this is this m value here. Okay, so we're going to compare the power, the highest power in the numerator with that of the highest power of the denominator. And I'll go with the same as we did in the notes. The graph will have a horizontal asymptote, okay? If A, so condition 1, condition or scenario 1, n could be less than m, okay? N could be less than m. And if n is less than m, if the power in the numerator is smaller than that of the denominator, then the line y equals 0 is the horizontal asymptote. Yeah? 2, so that's one scenario. What happens if n is equal to m? Well, if n is equal to m, when they're equal, if the powers are the same, then the line y equal to an divided by bn. The coefficients, the quotient of the coefficients will be the line, is the horizontal asymptote. And then the final condition here, what happens if n is greater than m? Well, if the numerator power is bigger than the denominator power, there is no horizontal asymptote. So horizontal asymptote, in my opinion, is sort of very easy to see. It's more visual than anything else. Okay? More visual. So I'm going to leave this here. Okay? I'm going to leave the conditions at the bottom. And let's see if we can look at an example. Okay? So let's take off this portion here. Suppose now I give it a function and I said find the vertical and horizontal asymptotes. If any, okay? If any. And the function we'll look at is f of x, yeah? F of x is equal to 2x squared over x squared minus 1. X squared minus 1. Well, we know how to find vertical. Vertical is taking the denominator, set it not equal to 0, and the value that we obtain, those will be the vertical. So let's look at the vertical. For the vertical, we said that x squared minus 1 cannot be equal to 0. So we'll add 1 to both sides. And we have x squared cannot be equal to 1. Okay? X squared cannot be equal to 1. But then we take the square root of both sides. Don't forget we'll get a plus or a minus. So x cannot be equal to plus or minus the square root of 1, which is equal to plus or minus 1. Okay. So what are my vertical asymptotes? Well, my vertical asymptotes, so the vertical asymptote here asymptotes, you have two of them now. X is equal to minus 1 and x is equal to positive 1. So we have two vertical asymptotes. Okay. Just as an extra activity from here, you could have also identified the domain, right? So you guys could tell me also what is the domain of this function. Now, we're also asked for the horizontal asymptote. Well, for the horizontal asymptote, we want to compare the numerator, okay? So n here for this example, n for this example, n is equal to 2, that's the numerator power, and m is also equal to denominator power is 2. So both numerator is equal to denominator. So we're looking at condition 2. then the line y equals the quotient of the numerator divided by the denominator, okay, leading coefficient. So here, the leading coefficient is a 2, okay? Leading coefficient here is a 2, and the leading coefficient here is a 1. So my horizontal asymptote is y equals 2 divided by 1, which is equal to 2. So the line y equals 2 is my horizontal asymptote. Okay. Y equals 2. So finding the horizontal asymptote, once again, we're comparing the power of the numerator with that of the denominator. If the numerator power is less than the denominator, it's the line y equals 0. For example, if this was a 1 and this was a 2, then you will have the 1 is less than 2, obviously. So y equal to 0. If this is a 3 and this is a 2, then it will be condition 3 and there will be no horizontal asymptote. Okay? So horizontal asymptote, not that difficult to identify. Now you could look at it also from infinity, right? As the x approaches that, as the y value approaches, sorry, not x, what happens? But I'm going to leave that part out in this video. I don't want to get into that, okay? For now, we'll just compare the powers of the function, okay? Only compare the powers of the function. Okay, so let's look at slant asymptote now. Let's look at slant asymptotes. So generally we say when the graph is an improper function, at least that's what I say, when the graph is an improper function. And I say that only because the denominator power is smaller. So let's look at slant asymptote. Slant asymptote. So sometimes you will see oblique, right? So we said in a slant asymptote, what we're doing is sort of like we can tell just by looking at the function. Okay? If I have the function f of x, and I'm going to take the example, the one that's I talked about in the notes or in the class notes. If we have x squared minus x over x plus 1. Well, if you notice here, the power in the numerator is a 2, the power in the denominator is a 1. Anytime the numerator power is bigger than the denominator power, you will have some slant asymptote. Okay? So, how do we figure out what is the slant asymptote? Well, so note, if the numerator power is larger than the denominator power, there is a slant asymptote. Okay? There is a slant asymptote. If the degree of the numerator if the degree of the numerator is greater than the degree of the denominator, then we have a slant asymptote. Now, since we're looking at linear, okay, that degree has to be exactly 1. One difference, because we're looking at linear. So how do we find it? Well, notice that this is the same if I fill in the missing terms. uh, x squared minus x plus 0, right? We don't have to write a 0, but it is quadratic, over x plus 1. You don't have to write a 0, but notice it's quadratic. So what we're going to do is perform long division. So x plus 1 goes here, and x squared minus x goes in there. And remember how we perform long division, right? What is x squared? Only the first term divided by the first term on the outside. So x squared divided by x, that is equal to x. And we write it above the x term. So x times x is x. X times 1 is positive x. Don't forget, we have to subtract. So because of that, this little plus sign here, when you distribute, will become a minus. And when you distribute here, this becomes a minus. So minus x becomes minus 2x. And then x times x, x times x, x times x. Let's redo this here because I made a little error here. Okay. This will be x. X times x is x squared. I had put x a few seconds ago. And x times 1 is plus x. Okay? So, because of we're going to always subtract, okay? When you distribute, this little plus sign here becomes a negative, and when you distribute here, this plus also becomes a negative. So what do we have? Minus x becomes minus 2x, okay? And this x squared minus x squared, they cancel out, it becomes 0. Well, don't forget I said there was a plus 0 there, so when you bring down, there is nothing to bring down, right? If you want to write a plus 0, that's fine. When you bring it down, you just write plus 0. And then we divide again. What is minus 2x divided by x? Right, the first term divided by the first term. If you want, you can review the notes on the video on long division. So this becomes minus 2. Okay? So if we put minus 2 here, above the constant term, minus 2 times x becomes minus 2x, and minus 2 times 1 becomes minus 2. And once again, don't forget we have to subtract. As you subtract, this negatives now become a positive, and this negative, a negative times a negative becomes a positive. 0 plus 2 is 2. This will cancel with that. Well, the slant, when we're looking for slant asymptote, what we're really looking for is this quotient. We don't care about remainders for slant asymptote. All we care about is the quotient. So the slant asymptote here, okay, the slant asymptote will be y equals, I said earlier it's written in the form y equal mx plus b, it'll be x minus 2, where the slope is 1, the y-intercept is negative 2. So this is some sort of a diagonal line. Okay, the line has a slope to it. Okay. So you can basically tell by looking at the equation also if there is a slant asymptote. Anytime the numerator power is greater than that of the denominator power by 1, we will have a slant asymptote. Okay. So now that we have the idea of slant asymptote, horizontal asymptote, and vertical asymptote, we have more tools available to us to graph rational functions now. Okay? More tools available to us. So we did long divisions prior, so I don't think that this here would be too much of a problem for you to understand what's happening. If not, review the videos on long division that I've created for you. And then once you perform long division, it's just the quotient. We do not care about the remainder for slant asymptotes, okay? do not care about the remainder. So that's all on rational functions. In my next video, we'll look at some more examples. Since the next video is on graphing rational functions. So we'll look at some more examples shortly and we'll see how it goes.